Hello, everyone. We are project number 2, and our topic is based on the paper written by Christophe Dorer on the topic Impact of Longitudinal Phase Matching Variations on Three-Wave Nonlinear Interactions. Three-wave mixing corresponds to the interaction of waves at different frequencies, say omega 1 and omega 2, and omega 3 is equal to omega 1 plus omega 2. This is widely seen in non-linear frequency conversion, primarily in second harmonic generation and optical parametric amplification, resulting in an energy transfer from the input pump at, say, frequency omega 3 to the signal and the idler waves at frequencies omega 1 and omega 2. Now, for efficient three-wave mixing, as we've discussed in class, this requires phase matching. And the condition for phase matching, as illustrated here, is that the wave vector mismatch, also known as delta K, should be, which is equal to K3 minus K2 minus K1, should be close to or equal to 0. And for perfect phase matching, it should be equal to 0. And this is the notation as elaborated here. Now, for collinear interactions, as again discussed in class, we take this relation along a common propagation axis, which is mostly the z-axis. However, if we expand our vision a little more, we can generalize the case for even transverse coordinates such as x and y. In most cases, the resulting wave vector mismatch which we obtain is independent of both the transverse coordinates as well as the longitudinal coordinates. But in cases where we can control the magnitude of the wave vector for individual cases, we can observe longitudinal variations, which can further enhance the nonlinear conversion, or in other words, it can increase the conversion efficiency. So for this, the paper utilizes specifically KDP or DKDP crystals, which in full form are deuterated potassium dihydrogen phosphate crystals, mainly because of the fact that we require a relatively higher aperture crystal for this experiment, which can easily be provided by these crystals. And these crystals are also currently one of the easiest to grow at the required large aperture. The choice of these crystals will be further elaborated ahead in this video. So in our project, we first quantify the performance of second harmonic generation and optical parametric amplification by applying normalized equations and a polynomial representation of our wave vector mismatch as a function of the longitudinal coordinate, which we generally take as z. After this, we estimate the impact of these spatial variations in the wave vector mismatch, and we do this for each of the 5 crystals which we've been graciously provided in the dataset by the author himself. So as a result of this paper, we conclude that minor longitudinal irregularities in the crystal of comparable quantity will not really affect the suitability of the crystal for second harmonic generation and optical parametric amplification.
So now we are going to discuss the simulation framework, which is basically the equations that we need in our project. We are going to analyze the nonlinear mixing of 3 waves at frequencies omega 1, omega 2, and omega 3 is equal to omega 1 plus omega 2. We start by assuming that the Markov effect, which means the divergence of the pointing vectors of the waves, is negligible. We also assume that the optical index of the waves is independent of the longitudinal coordinate z. So as the waves propagate from an initial reference frame at z is equal to 0 to a plane at coordinate z, they accumulate phase shifts kj into z, where kj is the propagation constant defined as kj is equal to nj omega j by c. Even if there are longitudinal variations in the optical index, they can be neglected if they remain small and they remain small within the region where z is nearly lambda j, where lambda j represents the wavelength associated with the waves. So in this case, the accumulation in the phase is given by phi j of z is equal to integration from 0 to z kj of z prime bz prime. The phase mismatch at coordinate z is therefore delta phi of z is equal to phi p of z minus phi 2 of z minus phi 1 of z. We have the equations dou E1 by dou Z is equal to I omega 1 d effective by Cn1, E3 E2 star exponential of I delta phi z. Dou E2 by dou Z is equal to I omega 2 d effective by Cn2, E3 E1 star exponential of I delta phi z. Dou E3 by dou Z is equal to I omega 3 d effective by Cn3, E1 E2 exponential of minus I delta phi z, where d effective is the effect of nonlinearity and C is the speed of light. It is important to highlight that a factor of 2 on the right hand side is absent. This is because of the author's convention that Ej of z comma t is equal to the real part of Ej exponential of I phi j of z minus omega j t, and Ej of z opposed to opposed to the convention that Ej of z comma t is equal to 2 into real part of Ej e power I into phi j of z minus omega j t, or Ej of z comma t is equal to Ej e power I into phi j of z minus omega j t plus its complex conjugate. We also write a delta k of x comma y comma z as this form, where the first term is delta k of xyz minus average value of delta k xyz, and the second term is the average value of delta k of xyz. The bracketed term showcases the longitudinal variations in wave vector mismatch from its average value. Deviation of longitudinal variation in wave vector mismatch from its average value. In the subsequent sections, we are going to quantify the influence of longitudinal variations in wave vector mismatch on linear processes. This process is considered to be phase matched when average value of delta k xyz is 0, and considered to be detuned from phase matching if delta k average value of delta k is not 0. And now we introduce normalized fields Ej as Ej is equal to capital Ej into root epsilon naught C n j by 2 h cut omega j into k. Here Ej represents the normalized field and k stands for a constant. We also introduce the concept of field intensity as Ij is equal to epsilon naught Cnj by 2 mod Ej square. It is important to note that the factor of 2 in denominator is introduced in accordance with the convention we followed here. We can see that Ej square is directly proportional to the number of photons at their respective frequencies. Additionally, we normalize the coordinate z by expressing it as z is equal to capital L into capital Z, where L represents the length of the nonlinear medium and Z, capital Z, is confined within the interval 0 to 1. Consequently, normalized phase mismatch can be written as delta capital phi of Z is equal to delta small phi of Lz. In a similar way, we write wave vector mismatch as normalized wave vector mismatch delta capital K of Z is equal to L into delta small k of Lz. To determine the constant K, we substitute the normalized field amplitudes, these amplitudes, into the coupled equations here. From the first equation, we can get dou E1 by dou Z is equal to I into LD effective by K root over 2 h cut omega 1 omega 2 omega 3 by n1 into n3 c cube epsilon naught E3 E2 star exponential of I delta phi c by setting K is equal to L d effective into root 2 h cut omega 1 omega 2 omega 3 by n1 into n3 cq epsilon naught, we can obtain these equations. And these normalized equations are very useful in many nonlinear mixing processes. Like, for example, we can use them in to model the evolution of a signal idler and pump waves in optical parametric amplification without having to account for individual frequencies and individual optical indices. We can also use them for type 2 second harmonic generation with E1 and E2 representing orthogonally polarized waves at omega and E3 representing upconverted frequency to omega. So for type 1 SHG, we can use these equations considering E1 to have a frequency omega, E2 to also have frequency omega, and E3 to have the upconverted frequency to omega. We get equations as follows. Dou E1 by dou Z is equal to I E3 E1 star exponential of I delta phi C. Dou E3 by dou Z is equal to I by 2 E1 square exponential of minus I delta phi C.
Before moving forward, we'll first use our framework to simulate second harmonic generation and optical parametric amplification in ideal phase matching conditions, which occurs when delta phi of z is 0 for all values of z. The intensities here are defined as the squares of the modulus of the normalized electric field. That's this. So, starting off with SHG. For SHG in particular, this phenomenon is refers to as matched of type 1, where fundamental frequency at omega 1 is upconverted to 2 omega when delta phi of z is 0 for all z. We start off by importing the necessary libraries. The array E1 of 0 represents the input electric field amplitudes. The array E3 of 0 represents the output field. We define the complex ordinary differential equations, and the function Rankata coupled performs one step of the Rankata method for the ordinary coupled ordinary differential equations. It takes in parameters and returns back the updated values after the iteration. Below that, we have the loops for all of the calculations. For each value in E1 0, it performs a set of calculations updating E1, Z, and E3. And this final, it also records the efficiency, and that is the thing that is plotted against the input, this. So one can see a rising trend increasing towards an asymptotic value of zero point 0.5. Using the quantum picture, you can see that the generation of one photon at 2 omega would require two photons at 1 omega. Thus, this plot is pretty consistent. Further simulations have been performed at I1 of 0 at 3, which corresponds to a photon conversion efficiency of 0.35, which is equivalent to 70%, and thus that has been highlighted on this graph. We can continue on to optical parametric amplification. So similarly, using the same framework, we can simulate OPA in the ideal phase match conditions. So here we'll be using the equations 11, 12, and 13 with delta phi as put as 0 with some initial conditions which I'll specify in a bit. So the output signal intensity is given by I1 of 0, I1 of 1, and the input normalized pump intensity is given by I3 of 0. So let's look at the code. The same as before, all of them have been normalized or initialized, I mean. Um, and the coupled differential equations and the ordinary differential equations have been defined. Now, to start off with, the normalized input signal and the idler intensities have been set to 10 raised to minus 3 and 0, which corresponds to an electric field of 10 raised to minus 1.5 and 10 and 0. So they are the same iterations have occurred and they have been plotted. So you can see at the typical exponential curve again, and after followed by a drop, which occurs due to reconversions. Further simulations have been performed at 2 points. One is at 100% pump depletion and one is at 50% pump depletion, and they have been highlighted here.
So now we are going to analyze the impact of longitudinal variations on in the three wave nonlinear mixing on the relative efficiency of second harmonic generation and the optical parametric amplification. So first of all, we approximate the longitudinal variations in delta kz, or the variation of delta k as a function of c, in terms of shifted Legendre polynomials. So we express the normalized wave vector mismatch as a function of the normalized longitudinal coordinate as a sum of shifted Legendre polynomials with these coefficients, these Legendre coefficients, which are taken from randomly from as the uniform distribution minus rho to rho, where rho itself is varying from 0 to 1. So the sum here is taken from for the first order polynomial to some nth order polynomial. The n values that we'll be considering today are 1, 2, 3, and 5, which are done with as done in the paper. So the reason behind choosing the legendary polynomials is that we want to approximate the wave vector mismatch as some polynomial, and the legendary polynomials seem to be the ideal choice because their integral over -1 to 1 is 0. So we know that delta kz represents essentially the bracketed term that we observed here. This term is represented by delta kz, and the integral of this term over -1 to 1 is 0. Once we normalize it appropriately, once we normalize the z coordinate, once we normalize the k, and so this bracketed term can be suitably represented by the delta capital K of capital Z once we take this form. Then so we'll be plotting for n is equal to 0 also. It might be a little confusing because the summation here itself is starting from 1, but n is equal to 0 just would represent a constant phase mismatch equal to rho. So rho here is the half of the length of this interval over which we are considering the legendary coefficients. So first we do this process for the second harmonic generation. So we analyze the impact of relative spread of relative efficiency for an SHG process, and we are operating at the point delta phi naught is equal to 0. That is the constant phase mismatch is 0, and I1 and I1 of 0, that is the normalized input intensity, is 3. And we saw earlier that the photon conversion efficiency in the presence of ideal phase matching conditions is 0.35 at this point. So we define relative efficiency as defined by the author as the ratio of the photon conversion efficiency in the presence of longitudinal variations to the photon conversion efficiency in ideal phase matching conditions. So whatever photon conversion efficiency we get for delta k varying with z, we divide that by 0.35 for this set of input conditions if we are considering this input condition, and so we'll get the relative efficiency for that particular polynomial delta k. So first thing we'll do is we'll analyze the variation in relative efficiency as a function of rho. Rho represents the range of the legendary coefficients, the coefficients of the legendary polynomials that we are taking in the expression of delta k capital Z. So I'll explain the code, but so for first of all, we have plotted just for n is equal to 1 just to show that our code works. And here we see that the difference in the minimum and the maximum is, so this is done for 100 simulations. So for each curve represents one simulation. So we see that, so this is a random process. So we'll get a spread in the relative efficiency. We see that the spread is even less than 0.5%. So it is clearer, we'll be able to analyze this in a much better way if we plot for all the n values together, which is done here. So what we are doing here is, for each n value, we are running 100 simulations, and in each simulation, we are taking 5 values of rho. For each value of rho, we obtain a set. For each value of rho, we have an interval minus rho to rho. From that interval, we choose a set of we choose randomly a set of coefficients which give us a polynomial delta kz. Then from that polynomial, we solve the coupled field amplitude equations to obtain the relative efficiency. So this gives us a set of 5 points for each simulation on the plane of relative efficiency versus rho. We observe that relative efficiency versus rho varies quadratically. So we obtain the best quadratic fit for the relative efficiency as a function of rho, and we do that 100 times. So this quadratic fit, best quadratic fit is done for each simulation, and we're running 100 simulations. So we get 100 curves for each n value, which represent a spread in the relative efficiency as rho varies. So we see that first thing to see is that n is equal to 0, which just represents a constant wave vector mismatch of rho. The relative efficiency for n is equal to 0 decreases much faster than higher polynomial orders. Then the total decrease in the relative efficiency, overall decrease in the relative efficiency for combining all orders is less than even 1%. Then another thing to notice is that as the n values increase, we see that the spread in the relative efficiency, that is the minimum and the maximum curves, the difference between them increases. This also increases as rho increases. Another thing is that the blue and the green curves nearly overlap. So this means that beyond the quadratic order, the longitudinal variations do not have a significant impact on the spread of relative efficiency. So the next thing that we do is we analyze the impact of relative efficiency impact of longitudinal impact of the root mean square of the sigma. We'll plot the root mean square of the wave vector mismatch. We'll plot the relative efficiency versus the root mean square of the wave vector mismatch, which we call sigma. So again, this is done here for one case, which is the n is equal to 0 case. This curve looks very similar to what we obtained for relative efficiency versus rho for n is equal to 0. Again, for a clearer picture, we obtain all the curves together and then analyze them. So again, as was seen in the case of rho, the decrease in the relative efficiency for n is equal to 0 versus sigma is much faster as compared to higher order polynomials. The green, the minimum, so the maximum of the green, blue, and yellow curves are almost similar. But another thing to notice is the minimum of the green, blue, and yellow curves nearly overlap. So this means that again, with an order greater than 2, the longitudinal variations do not have a significant impact on relative efficiency. Another important thing to note here is that the minimum and the minimum and the maximum of for n is equal to 1 nearly overlap. So there is approximately 0 spread in relative efficiency for n is equal to 1. Now this happens because for n is equal to 1, the relative efficiency, the wave vector mismatch varies linearly in Z. And so the wave vector mismatch, the RMS of it has a 1-to-1 relation with the legendary coefficient that we are choosing from minus 2 to 1. This leads to this nearly zero spread, which was also seen in the case of n is equal to 0. So then we choose to analyze so now all of these simulations for relative efficiency versus rho and relative efficiency versus sigma were done for delta phi naught is equal to 0. Now we add a constant phase mismatch delta phi naught, and now the longitudinal variations are still present, but now rho is fixed. Rho we take to be 0.5 now. And we choose the coefficients of the Legendre polynomials randomly from this uniform distribution minus 0.5 to 0.5. And then we analyze the impact of relative efficiency with a varying delta phi naught. So again, as we did for sigma and rho, we do this for n is equal to 0 and n is equal to 1 case. So here so black dots are not even visible, but black is chosen for n is equal to 0 and they nearly overlap. So it would be clearer if we just plot all the n values together, relative efficiency for delta phi naught together. So we see here that the spread is pretty much very high, is considerably larger as compared to n is the lowest orders. For the spread for higher orders is considerably higher than the spread for lower orders. So this is again even more clear if we just zoom in around the center of this curve. So delta phi naught here varies from 0 to 2 pi. And so if we zoom in around the center of this curve, we see clearly that first of all, for higher orders, the spread is the maximum. There is some spread for n is equal to 1 as well, and the n is equal to 0 is just one line here. But the spread for n is equal to 1 is considerably less as compared to higher n values. And again, for the green, yellow, and the blue dots are extending out to approximately the same length about the center. So that just means again that for higher orders greater than n is equal to 2, you do not see a significant impact of delta phi naught on the spread of relative efficiency.
Okay, now we'll analyze the variation of relative efficiency with respect to the same parameters that are rho, sigma, and delta phi naught, but for the case of OP. In this case, we have 3 waves with frequencies omega 1, omega 2, and omega 3. Here we have taken omega 3 to be the pump, which is the input. Then we have omega 2, which is the idler wave, and omega 1, which is the signal. For our simulations, we have considered 2 points, which were the 2 points marked in the section 2 clause for OPA, which correspond to 50% and 100% pump depletion. So basically, we have taken I20 to be 0, that is, there is no idler wave at the beginning, and we have taken I10 to be constant, which is 10 to the power minus 3, that is the pump frequency, and which is the signal frequency, and we are varying I30 for 2 points, which is 45.5 and 32.5. So I10 is equal to 42.5, corresponds to 100% pump depletion, whereas I20 is equal to 32.5, corresponds to 50% pump depletion. So 45.5 and 32.5. In this case, we have considered the variation for these 2 points, and let us start with the first graph, which is the variation of relative efficiency with rho. Just to remind ourselves, rho is the extent, or it is the maximum value of the Legendre polynomial coefficients. So basically, we'll be drawing the Legendre polynomial coefficients from a uniform distribution from minus rho to rho. So we first create the functions delta k, delta phi as we did before. And now in this case, we have 3 differential equations, coupled equations, and we solve them using the Runge-Kutta method. And once we solve them with the given initial condition, that is I20 is equal to 0, I30 is equal to 45.5, and I10 is equal to 10 to the power minus 3, we get this plot, which shows the variation of the relative efficiency with rho for the 100% pump depletion case. In this case, we have done 100 simulations. By 100 simulations, we mean that for each value of n, we have made 100 plots. And basically, the capital N here refers to the degree of the Legendre polynomial expansion of delta k. So basically, when we say n is equal to 5, we consider Legendre polynomials up to order 5 for an expansion of delta k. So this is the plot we obtained. One thing to notice here, which is different from the SHG plot, is that the variation in the efficiency with rho is very less as compared to SHG. So basically, there is not much decrease in the efficiency as we increase the value of rho. And another difference is that there is no significant dip in the efficiency for the n equal to 0 case. Basically, if we recall, for the SHG case, there was a sharp decrease in the efficiency for the n is equal to 0 case, whereas for the other orders, the efficiency was not decreasing much. It was decreasing by less than 1%. But in this case, the decrease is less even for the n is equal to 0 case. And the other thing is that, so basically the decrease is less, overall less, and it is not as profound for the n is equal to 0 case. Then a similar plot for the 50% efficiency case is shown here. In this case, we see that the dip for n is equal to 0 is actually significant as compared to the other orders. And we see that for the other orders, the decrease is not as much as it was in the case of SHG. But in the first graph, we saw that the minimum for the higher orders, that is the higher values of n, can actually lie, it can be comparable with the n is equal to 0. Then we next analyze the variation of the relative efficiency as a function of sigma. Sigma here refers to delta k RMS. So basically, we have just created a function to calculate delta k square, then delta k RMS, and here is the function to which takes the input, which takes the boundary conditions, and then solves the differential equations to give us the plot. This is the plot we get. Now again, we need to notice here that the dip in n is equal to 0 is not actually so much. In fact, the dip is more in some cases, the dip is actually more for the higher values of n. So till now, we saw that the minimum efficiency was actually achieved for n is equal to 0, but in this case, we see that the minimum is actually achieved for higher values of n as well. Another thing to notice is that, so as if we recall, for each value of n, we have plotted 100 simulations, right, for 100 plots. But we see only one curve for n is equal to 0 and n is equal to 1 case. This happens because all the 100 plots for these two values are actually coinciding with each other. That is why we see just one line for n is equal to 0 and for n is equal to 1. This was the case for SHG also. But we do see a good spread for the other values of n, and in fact, their minima lies below n is equal to 0. So this is something new which was not seen in SHG. And a similar plot for the 50% depletion case is this one. Here also we see that the dip is now actually again significant for the n is equal to 0 case, but this dip is actually comparable with the minima of the other n values. Then the third thing we have to plot is the variation of relative efficiency as a function of delta phi naught. If we recall, delta phi naught was the constant part which was not varying with z, the constant part of the wave vector mismatch, which is delta k. So in this case, for the varying part, that is the sum of the Legendre polynomials, we have fixed the uniform distribution to be from minus 0.5 to 0.5. So we are basically getting the coefficients of the Legendre polynomial expansions from this fixed uniform distribution, and now we are varying delta phi naught. So again, we have delta k, delta phi, we have the three equations, and once we solve them and we plot the relative efficiency as a function of delta phi naught, we get this plot. So this is similar to what we got in the case of SHG, that is the relative efficiency is decreasing with delta phi naught. But one difference to note here is that if we recall, in the case of SHG, there was a nice spread in the relative efficiencies for a given value of delta phi naught also. So basically, there was a spread for the higher values of n. The plots for n is equal to 0 and n is equal to 1 were more or less coincident with each other. But for the higher values, the values were actually varying for the 100 simulations. But in this case, we see a very nice a very narrow plot, which shows that all the values for all values of n are actually coinciding with each other very well. So this is something different from the SHG plot. And now we are varying delta phi naught from 0 to 4 pi instead of 0 to 2 pi. This is a zoomed in version of the same plot, just to make things clearer. So again, we see that the spread is actually there, but the spread is actually there for the higher values of n. So basically, we see that the points on the outer side of this curve are actually blue dots, which correspond to n is equal to 5. So the spread is actually there, but it is much less as compared to the SHG case, and that is why in the previous plot it is not so visible. Then we do a similar thing for the 50% depletion case. Again, we see a decrease in the relative efficiency with delta phi naught, and again the spread is not as much as it was in the case of SHG. And similarly, a zoomed in version of the same also shows us that the spread is actually there, but it is there only for the higher values of n, not for the lower values of n. So this is our analysis for the variation in relative efficiency for the same three parameters, that are rho, sigma, and delta phi naught for the case of OPA. So basic differences which we notice here are that first, the minima is not necessarily obtained for n is equal to 0 case. In fact, in some cases, the minima for the other values of n can actually lie below the n is equal to 0 curve, which means they might give a lower efficiency than the n is equal to 0 curve, which is the constant wave vector mismatch. Then the other thing to notice is that the variation is not as much as it was for the case of SHG. The decrease was not so profound as a function of rho. And the third thing we notice is that the spread is actually less for the relative efficiency versus delta phi naught curve as compared to what it was for the SHG case. So this ends our discussion for the variation of longitudinal variations with rho, sigma, and delta phi naught for both the cases SHG and OP.
Moving on to section 4, application to 5 DKDP crystals. In section 4, we observe the transverse wave vector mismatch variations as measured on 5 deuterated potassium dihydrogen phosphate crystals. These are processed to estimate the effect on the efficiency of second harmonic generation and optical parametric amplification in these crystals with similar longitudinal variations. To begin with, let us discuss the choice of these crystals for this paper. Most nonlinear optics applications are based on crystals with generally high dimensions and higher apertures, but much larger crystals are required for high energy laser pulses. Frequency conversion of high energy laser systems is based on large aperture potassium dihydrogen phosphate and its partially deuterated isomorphs, which is DKDP crystals. KDP and its isomorphs are currently the easiest crystals to grow as well at very large apertures as required in this paper, and they possess the required local variations in deuteration level. So all of these properties make it suitable to be utilized in this paper. Presently, there is no non-destructive method which is available to directly assess the longitudinal fluctuations in phase matching conditions within nonlinear crystals. So we've decided to use experimental data which pertains to transverse phase matching variations as determined from energy detuned second harmonic generation processes. As mentioned earlier, these are the characteristics of the 5 DKDP crystals which we are utilizing through our data. As visible again, each crystal has a different deuteration level. Crystals 1 and 2 are deuterated at 70%, crystal 3 at 80%, crystal 4 at 92%, and crystal 5 at 98%. And as mentioned earlier, according to transverse dimensions, the transverse length of the aperture of crystals 1 and 2 are 48 millimeters, and the aperture length of 3, 4, and 5 are 22 millimeters. When dealing with minor fluctuations in the wave vector mismatch, we observe that in the dataset, the value of the wave vector mismatch represented as delta k as a function of the transverse coordinates x and y. This is considered to represent the average across the longitudinal variable z as well. This presumption is also valid in our observations, which we will be seeing soon, because the variations in delta K are consistent with the measured data as well. And the second harmonic generation energies align closely with the values which we are computed based on the average wave vector mismatch that we've used here. So here primarily first we are importing all our required data sets and storing them as data frames using the Python library pandas. And further on, we are proceeding to plot the values of delta K SHG, our wave vector mismatch that we obtain, to get a general idea of the kind of data that we're dealing with. So the transverse variations in delta K for second harmonic generation at this particular wavelength of 1053 nanometers for the 5 DKDP crystals have been plotted ahead as heat maps to understand the range of the values of the wave vector mismatch that we will be dealing with. This is the plot for crystal 1. This is the plot for crystal 2. This is the plot for crystal 3. This is the plot for crystal 4. And this is the plot for crystal 5. So these 5 heat maps give us a rough idea of the kind of delta K values which are there for each crystal in our data set. And this dotted line which you see here represents the lineouts which we will be utilizing soon, that they'll be coming up soon. These represent the division according to which we'll be taking lineouts later on for our delta K values to calculate Legendre coefficients. Moving on, specifically for section 4.1, we plotted the average magnitude of the wave vector mismatch, which is our delta K SHG, at all the transverse points x, y within the aperture of each crystal as relative to its value at the center of that particular crystal. So the data sets that we were provided had 2 different kinds of data for each crystal. It had a set of delta K values for every transverse point x, y for each crystal. And it also had the values of x, y or of the various transverse points for each crystal. So we utilized those 2 data sets as shown earlier in the CSV files, and we calculated the average magnitude of the distances and the average magnitude of the wave vector mismatch as follows. Firstly, we determined the absolute value of the difference between the delta K SHG at a given transverse point x, y with reference to the center of that particular crystal and the value of delta K SHG corresponding to the center of that crystal. Now, for all the crystals, the value at the center value x, y was not exactly 0, 0. Some of them were of the order of 10 raised to minus 15, but they were pretty much close to 0. So we located those values and we used those exact points of x, y as the center of the crystal and calculated the distances of each point respectively. So here we first calculate the absolute difference between the delta K SSG values of any transverse point with respect to the delta K value at that center of the crystal for every individual point for each crystal. This helps us to determine how much each point's wave vector mismatch deviates from the center value as defined. After this, the paper specifies that we have to classify all the values of delta K as a function. We have to bin them as a function of distance from the center, to be precise. So we organized all these differences into bins, which is based on the distance of each point from its center. So say that if you have a given circle and a radius, so at a given radius, whichever points in our data set were located on that circle, we classified them into a particular bin. And after that, we averaged all the respective values within that given bin to determine a single value for a single given distance. This is again following the procedure as mentioned in the paper. So this also reveals the typical change in the measured wave vector mismatch for points which are located at similar distances from the center. Again, determining an averaged value for a given distance from the center of the crystal. Finally, we plotted all these values graphically to demonstrate how the average wave vector mismatch varies as we move away from the center of the crystal. And the results of that plot can be seen as follows. This is the graph that we obtained. And as you can see, the crystals are colored accordingly. So from this graph, we observe that crystal 1 had a significantly low variation in the value of delta K as compared to crystal number 2. Specifically, I'm relating these two because crystal 1 and 2 have the same aperture length of 48 millimeters. As for crystals 3, 4, and 5, we notice that there's a maximum variation in value for crystal number 5, and crystal number 3 and 4 are relatively similar in their variation, as we can see over here. One point to mention in this case is that we can perform multiple scans on each crystal through slight variations, such as rotations through 180 degrees. But these measurements can yield slightly different values, but the trend is essentially more or less the same. We were provided with only one data set by the author. And anyways, since additional sets were not considered augmented to the insights which were gained, so we proceeded with this. And hence, in comparison to the paper, we've received a single line for each crystal as compared to 3 lines in the paper. But the observations which we've received are consistent with the observations that are observed in the paper itself. After this, we plotted the linear coefficient versus the deuteration level of each crystal. The linear coefficient is essentially, on an average, the slope of the previous graph that we obtained. Essentially, it's the value of delta K divided by the value of the distance, as we can even determine from the units of this linear coefficient. So upon plotting it as a scatter plot on an average, these are the values that we obtain. So we see that crystals 1 and 2 having the same deuteration level. We see that as expected from the previous graph, we saw more variation in 2, which is also observed here. The linear coefficient of crystal 2 is higher. And similarly, the linear coefficient of 3 and 4 is nearly similar, with a significantly high linear coefficient in crystal 5. So from this, we can estimate and we expect that as the deuteration level increases, there's a significant increase in the linear coefficient. We also notice a mild dependence on the variation amplitude with deuteration level. As mentioned, with higher deuteration levels, larger variations are observed. And to again stress upon this, we plotted the third graph, which was variation of standard deviation versus the deuteration level. The standard deviation was calculated across all values of delta K for each crystal. And again, as observed here, there is the standard deviation of crystal number 2 is higher than crystal number 1 slightly. The standard deviation of crystal number 3 and 4 are nearly similar as expected from the first graph. And the standard deviation of crystal number 5 is significantly high. Based on this, we can conclude that as the deuteration level of the crystal increases, the variation of the values of delta K across each transverse point in the crystal increases significantly. These values were determined by linear transfer scale of the data set, and we scaled it to a length of 10 millimeter, as mentioned here, by multiplying by 10 and dividing by the original length of the aperture of the crystal itself, which was 48 millimeters for 1 and 2 and 22 millimeters for 3, 4, and 5. So as a result, the scale standard deviation shows similar variations for crystals 2, 3, and 4 as we expected, and lower variations for crystal 1, again, as expected, with not much of a change as visible in the first graph. And there's a very, very high variation for crystal number 5, as again expected from the first graph itself.
In this section, we will be fitting each of the obtained normalized longitudinal wave vector mismatches by a sum of Legendre polynomial and obtain the coefficients corresponding to each term of the polynomial. And these coefficients are then used as an experimental benchmark for comparison to the simulations obtained in section 3. In the case of SHG, integration length is chosen to be 12 mm based on the typical thickness of SHG crystals used in lasers generating high energy nanosecond pulses. So our approach involves extracting lineouts from the experimental data, which represents variations in wave vector mismatch over this 12 mm span. For the 3 small aperture crystals, we have chosen 4 specific lineouts that extend either horizontally or vertically from the central point of the aperture in various directions: x greater than 0, x less than 0, y greater than 0, and y less than 0. Whereas for the two large aperture crystals, we have chosen 8 lineouts 4 along vertical and 4 along horizontal, and that gives a total of 28 sets of delta K for SHG. Now, each of these generated lineouts are fitted by legendary polynomial of degree 10. So, the utility of plotting fitted coefficients with polynomial degrees is to show that the coefficients have low values, and in particular that the observed variations are mostly low order. These coefficients remain consistently below 0.25 across all orders. Beyond order 5, it is smaller than 0.01. This supports the simulation results obtained in figure 2, explaining the exclusion of higher orders greater than 5, that longitudinal variations have no significant impact on the SHG process for a crystal that is either nominally phase matched or detuned from phase matching. Next, we perform the same analysis, but for the case of spectrally degenerate OPA pumped at 526.5 nanometers. In this case, the typical integration length is 48 mm, and two lineouts are chosen for each crystal, one horizontal and the other one being vertical, spanning the distance of 48 mm. So that gives a set of 4 lineouts. Comparison of these lineouts with the range of coefficients covered by the simulations in figure 3 and 4 indicates that the OPA efficiency is not expected to be significantly impacted. Next, we analyze the wave vector mismatch at wavelengths other than 1053 nanometer. For evaluating the wave vector mismatch at different wavelengths, we utilize the experimentally determined wave vector mismatch variations at 1053 nanometer by considering the impact of variations in the local angle of the crystal relative to the propagation axis and the deuteration level. That is, wave vector mismatch can be induced either by the variations in the internal angle of the crystal, that is theta, or the deuteration fraction x. So this is the equation we have. Now this term is obtained on taking partial derivative of delta KSHG with respect to the phase matching angle, and this term is obtained on taking partial derivative of delta KSHG with respect to the deuteration level. So now to estimate the partial derivative with respect to theta, we need to find the partial derivative of the extraordinary index with respect to theta at the wavelength of lambda 3. And extraordinary index is theta dependent according to this relation, where the refractive indices NO and NE are wavelength dependent and are calculated using the Selmayr equations. For deuteration level equal to 70%, this partial derivative of extraordinary index comes out to be minus 0.039, and hence this is our final equation, which is dependent on lambda 1. Next, for estimating the partial derivative of delta KSG, that is wave vector mismatch with respect to the deuteration level, we need the indices generalized for arbitrary deuteration levels, for which we can use either of the two methods. In method 1, we use the idea of interpolation or extrapolation of indices at two reference deuteration levels. While method 2 involves assuming that partially deuterated KDP crystal is a mixture of pure and fully deuterated KDP. the refractive index of partially KDP with deuteration fraction x can be approximated using the Lorentz equation, which is expressed as this, where L and H are the two referenced deuteration levels, and N of L is the absolute refractive index, and rho of L is the mass density with a deuteration fraction of L. This approach yields similar results as the susceptibility average, that is method 1, which is attributed to the fact that KDP and DKDP have essentially the same mass density. So hence the bracketed quantity in equation is equal to minus 3 into 10 to the power minus 3 in 70% DKDP. So we are left with this as our final equation. So for a certain range of wavelengths where the partial derivatives in this equation remain relatively stable, it is observed that variations in crystal properties like its angle and deuteration level follow similar trends concerning phase matching. These variations are influenced by the ratio between the wavelength used for characterization, which is 1053 nanometer, and the actual SHG wavelength, which is lambda 1. The partial derivatives undergo change by around 10% over a 100 nanometer range centered at 1053 nanometers. This means that characterizing the crystal properties at 1053 nanometer can give us a pretty good idea of how the crystal will perform at other wavelengths in this range. In the case of non-degenerate OPA, the only difference is that it is operating at signal, idler, and pump wavelengths. The variation in wave vector mismatch is expressed as this. The angular partial derivatives is similar to the one obtained for SHG, which implies that local variations in angles have a similar impact on both of these nonlinear processes, and the partial derivative with respect to deuteration level is evaluated using the interpolation method along with the Selmayr equation for OPA pumped at lambda 3 equal to 526.5 nanometers. So depending on the wavelength of the signal, changes in the deuteration level have different effects. The partial derivative shifts by roughly 20% between 800 and 1053 nanometers. So when it comes to characterizing SHG with this wavelength range, we can trust it to predict the wave vector changes for a broadband OPA that operates in this region. But if the signal wavelength strays far from its optimal value, this prediction becomes less precise. In a nutshell, our project focuses on how variations in wave vector mismatch along the crystal's length affect second harmonic generation and optical parametric amplification. We found that smaller variations have the most impact on efficiency, particularly for processes that are phase matched. These minor changes lead to reduced efficiency. However, processes that aren't perfectly phase matched show a wider range of efficiencies around the average. By looking at the transverse variation in the wave vector mismatch in 5 kdp crystals, we can estimate the longitudinal variations. Comparing these estimates with our simulations, we realize that longitudinal variations don't significantly affect three wave nonlinear mixing.